One of the most important steps in developing a simulation is defining the physics. When dealing with a model that involves multiple physical phenomena, there are three main modeling approaches we can use to couple the physics together. The first and recommended way is through adding built-in multiphysics interfaces. COMSOL Multiphysics has several predefined multiphysics couplings available. When you select and add the multiphysics interface to your model, the single physics interfaces are added and the multiphysics features are automatically implemented with the recommended settings. You can also define the physics using the sequential approach, where you define and run a single physics analysis to start, and then decide to add a second physics to your model. You can implement the multiphysics coupling using the Add Multiphysics window or the Multiphysics node. Lastly, you can use the manual approach to implement custom multiphysics effects within the physics interfaces in your model. This is done by manually including the dependent variables from one physics interface into the settings for another physics interface. In this video, we will show you how to define the physics for a multiphysics problem using these three approaches. Additionally, we will discuss the advantages and benefits provided by each. Here in the Model Builder window, you'll notice we have three components in this model, and we're going to be using each of these components to show you the different ways of setting up a multiphysics model. In the first two components, we'll be using the thermal bracket tutorial model, which can be found under Windows, Application Libraries, Structural Mechanics module, under Tutorials, and then you can open that by selecting Bracket Thermal. In the last, third component, we're going to use a different combination of physics to demonstrate the use of the manual approach. So we're going to show all three different multiphysics modeling approaches through these three components. Let's start off with using the built-in multiphysics interfaces within COMSOL Multiphysics. So we know what's happening in our model. This is a thermal expansion problem, so we can add the physics for that using the software's pre-configured multiphysics interface. This is always the option we recommend since it most efficiently adds all of the physics and multiphysics couplings to your model. And to add the multiphysics interface, it's the same process that you would use to add any other physics to a model. You go in the Physics tab, click the Add Physics button, and here we can navigate to our multiphysics interface. We can go under Structural Mechanics and select and add thermal stress to the component. So we can click that button again to close the window. And you'll notice when we added the thermal stress multiphysics interface, all of the physics, including the couplings, were added at once. So here under the multiphysics node, we have first thermal expansion. And in our multiphysics coupling node, we always need to specify where the multiphysics interaction is occurring. Here through our domain selection, it's applied to all domains. Then we want to specify the properties of the multiphysics interaction, which we would do here under the thermal expansion's properties section. Specify the input type as well as various other properties. And lastly, we want to specify the physics involved in the actual multiphysics coupling. So you'll notice for heat transfer and structure, both of these have drop-down menus, which include any applicable physics interfaces that we have already added to our model. We are pulling the thermal aspect of the problem from our heat transfer interface, and then the structural aspect from solid mechanics. Then we have the temperature coupling node, and this uses temperature from whatever we specify as the source interface to evaluate material properties in the destination physics interface. And again, these are both drop-down menus that include applicable physics interfaces you've already added to the model. So using the built-in multiphysics interface provides several benefits. It completely streamlines the workflow and process of adding and defining the physics for your problem. All of the physics are automatically coupled, and we don't need to remember which multiphysics coupling nodes specifically that need to be added. Also, when we use a built-in multiphysics interface, specific or modified settings are automatically included with the physics interfaces as well as the coupling features. For example, solver settings or element discretization settings. Right now, the discretization section isn't displaying, so we can go in the Model Builder window, click the Show button, and then select Discretization. We can expand that section, and then you'll see the specific settings for that, as well as for our heat transfer interface. So specific settings for this and other aspects relating to the computation of your problem will automatically be taken into account whenever you use a built-in multiphysics interface. So another way that we could have defined the physics is through using the sequential approach. And through this method, we add and set up our two physics interfaces individually and thereafter add the multiphysics couplings. So if we had defined the physics this way, we would have first added solid mechanics, defined the physics for this interface, and then solved and validated the structural problem in one study. After that, we would then add the heat transfer in solids interface, and again we would repeat this process by defining the physics for this interface and then solving and validating the thermal problem in a second separate study. You'll notice also after we added this second physics interface, a multiphysics node has been added to our model tree. Here we can add the multiphysics features we need by right-clicking the node and selecting and adding thermal expansion, as well as the temperature coupling. And then we would go in, and just as I mentioned before, we specify where the multiphysics interaction is occurring, define any necessary properties for the multiphysics effect, and then specify the physics interfaces to be coupled. And again, repeat this process for any other multiphysics features you've added. So in using the sequential approach, you can solve and validate the physics one at a time before solving the full multiphysics problem. We recommend utilizing the built-in multiphysics interface for your model whenever possible, since the ideal settings automatically included in the built-in multiphysics interface are not included when you use the sequential approach. For example, if we check the element discretization setting in our heat transfer in solids interface, we can see the option selected for the discretization and compare that to the option selected when we used the built-in multiphysics interface, and we have a different setting for discretization here. Specific settings that provide benefits with respect to the computation of the multiphysics model are not included in the sequential approach, while they are included when you are using the built-in multiphysics combination. For more information on element discretization and the reasoning for such differences, please see our blog post regarding the element order in multiphysics models. Also, please note that even if you've already added your physics individually using the sequential approach, you can still take advantage of the benefits provided through it if you had used the multiphysics interface by using the Add Multiphysics button. So first, I'm just going to delete these two coupling nodes we added to demonstrate this. We can find the Add Multiphysics button under the Physics ribbon. And this, in turn, opens the Add Multiphysics window. And here, multiphysics couplings will vary depending on the physics that are included in your model component. You can see in choosing to couple both the solid mechanics and the heat transfer physics, the multiphysics coupling we have available as an option is thermal stress. Let's say we added another physics interface to our model. Let's add electric currents. And if we return back to the Add Multiphysics window, you'll see if we were deciding to couple all the physics, we have a new option, Joule heating and thermal expansion. And again, this will always vary depending on the physics that we decide to couple. So perhaps we decide to decouple the structural aspect of the problem. We're provided with Joule heating, as well as equilibrium DC discharge. Perhaps we have solid mechanics and just electric currents. The option always updates depending on what physics you decide to couple. Let's say we want to add Joule heating and thermal expansion. We first have the thermal expansion multiphysics coupling. We also have an electromagnetic heat source coupling, which passes the resistive heating from the electric currents interface to the heat transfer interface. We have a boundary electromagnetic heat source multiphysics coupling, which represents the electromagnetic surface losses, which passes electromagnetic losses as a heat source from the electrical aspect of our problem to the thermal aspect. And again, we have a temperature coupling, passing the temperature field from the heat transfer interface to the electrical interface. And then we'll want to do the same, pass the heat transfer temperature from that interface also to the solid mechanics interface. So in using the built-in multiphysics coupling through the Add Multiphysics window, let's check again and see if the discretization setting for our heat transfer interface updated. And you'll see that it has. So please note that adding the coupling through the Add Multiphysics window will include modified settings that are ideal for computing the combination of physics included in your simulation. Lastly, another way we can define the physics for a multiphysics problem is through manually setting up the multiphysics couplings using model inputs or expressions that include dependent variables or other expressions from another physics interface. To demonstrate this approach, as I mentioned earlier, we'll be using a slightly different geometry. We have a block, and let's use some different physics interfaces. So let's add fluid flow, let's add laminar flow to the component, and let's also incorporate heat transfer. So under heat transfer, add heat transfer in fluids. So when coupling physics using this approach, you first want to think about how the physics affect each other, then add the appropriate model inputs, and lastly, edit or replace any constant values within an expression to administer the coupling from one physics interface to the other. After adding the physics interfaces to your model, be sure to note in the conservation law or material model node, the model input section. Applicable fields in another physics interface that can serve as inputs in this physics interface will automatically appear as an option in the model input section. So currently there aren't any applicable fields from other physics interfaces included in this component that can serve as inputs to this interface. Although this physics interface provides us with the velocity field and pressure of the fluid flow in the model. If we go to the conservation law node under our other physics interface, heat transfer and fluids, you'll see we have two model inputs available, absolute pressure and velocity field. And each of these has a drop-down menu, and you can see that we can actually specify the absolute pressure and velocity field. This couples the laminar flow interface to our heat transfer and fluids interface one way. So this is a way of showing you how you can use the model input section in your physics interfaces to couple the physics involved in your model. Now, if we were to add as a material for this model a fluid that had temperature-dependent properties, consequently, this will affect the flow. So then we'll want to also couple the heat transfer and fluids interface to the laminar flow interface. And we can do this by using expressions for the material properties in any material that we add that include dependent variables from the heat transfer and fluids interface, which in this case would be temperature. So the variable T. If we add any material to the model, click Add Material, and let's say we wanted to add, we could add air. Let's say we wanted to add water. You'll notice in the Material Contents table, we have several properties, all dependent on the temperature. And these properties are defined in the respective basic property group, under which temperature is included as a model input, which was done by going under Quantities, expanding the Model Inputs branch, and then you just simply select the input, which in this case was temperature, add that, and then you can incorporate the variable T into the expression for the material properties. So now that we have a material that is temperature dependent, if we return back to the conservation law node under our laminar flow interface, you'll see now we have a model input of temperature to specify. It can be set to user-defined, wherein you enter a value or expression, or we can have the temperature field pulled from our heat transfer and fluids interface, HT3, by simply selecting it from the drop-down menu. So this demonstrates coupling through using expressions that include a dependent variable or other expressions from another physics interface. So this is a way of showing you how you can both utilize the model input section as well as utilize model inputs within the material properties themselves to administer coupling between the different physics interfaces in your model. And this approach is mostly useful for cases when such predefined couplings are not available. So now that we have gone through the different ways in which you can add the physics to a multiphysics problem, let's finish up by defining the physics for our original multiphysics problem, which would be the thermal bracket tutorial model. And this is used in both component 1 and component 2. Since we have already added all the same physics and multiphysics couplings in both, we only need to demonstrate defining the physics in one of them, since it would be the exact same setup. Let's use component 1, where we used the built-in multiphysics interface. So under our solid mechanics interface, we'll want to add a roller boundary condition and apply it to the two boundaries under our mounting bolts. Then we'll also want to add a spring foundation boundary condition to the surfaces of the mounting bolt holes. We'll want to change the spring type to diagonal, enter the values for those diagonal entries, and that's all set. So now we can move on to the thermal aspect of the problem. We'll want to add a heat flux boundary condition, and we'll want to apply it to all boundaries except for the two near the mounting bolts. Apply a convective heat flux of 10 watts per meter squared Kelvin. Then we'll add another heat flux boundary condition, this time applied to those same boundaries we omitted from earlier. Leave the setting to a general inward heat flux of 10,000 watts per meter squared. If we skip to solving the model, so we expand the study node, go in and make sure we have the correct physics interfaces and multiphysics couplings selected, and click Compute. And if you want any additional information regarding how to define the physics in a model or the process of adding boundary conditions, please see our tutorial video on assigning the physics to a model geometry in COMSOL. And you can see the results for stress, thermal expansion, and the temperature distribution in that bracket assembly. With that, we have showed you the different modeling approaches through which you can define the physics for a multiphysics model. This included utilizing the software's pre-configured multiphysics interface, using the sequential approach, and by manually implementing multiphysics effects within the physics interfaces added to your model. We also went over the strengths of using each approach. When using the software's pre-configured multiphysics interface, this adds all the physics at once, automatically couples them, and includes any modified settings best suited to compute the model with the physics you have added. Through the sequential approach, you are able to define, solve, and validate each individual physics setup in your model before solving the full multiphysics problem. Lastly, the manual approach enables you to implement a custom multiphysics coupling that is not built-in or otherwise available. Whenever possible, we always recommend that you take advantage of the pre-configured multiphysics couplings available within COMSOL Multiphysics. These enable you to most quickly and efficiently set up the physics in your model.